Hello students, I am Dr. Srivastava, Associate Professor SCIT Jaipur. Today we are going to learn how to plot Poisson distribution. A Poisson distribution is a discrete distribution that shows how many times an event is likely to occur within a specified period of time. We have conducted an experiment in the quality control lab to demonstrate the Poisson distribution. In the lab, we have taken a bowl containing 300 matchsticks, out of which 280 are non-defective and 20 are defective. An experiment is performed with drawing 10 matchsticks at one instance. After noting down the number of defective matchsticks, they are put back in the bowl. The process of drawing the matchsticks is repeated 10 times. Experiment observations are documented in the below table. We have to determine the experimental and theoretical probability for detecting the defects and to draw the Poisson distribution curve. So let's see the data that has been obtained during the experiment. In the first trial 10 matchsticks have been drawn, and out of which we have seen all are okay. Then the second time all are okay. Then the third time we have seen three defectives are there. Fourth time all are okay, only the one defective. So likewise this experiment has been repeated 10 times. For obtaining the experimental probability, first we have to determine how many number of defectives that are obtained in each sample. So for doing this, because as this experiment has been repeated 10 times, so for each trial we have to determine the number of defectives. So for finding the defectives, we may make use of the function countif. Then I have to select the range. So you can just select the range from here, and we want to determine the count of the defectives. So I just type the word defective. So here there is 0 defective. I can drag it down. So in the first two trials there is a 0 defective. No matchstick has been found defective. In the third, we have found one matchstick has been found. Three matchsticks have been found defective. So likewise, we have determined the defectives percentage. Now for finding the defective number or x, because our x is the what is the we are interested in finding the how many times in these 10 trials we have obtained the 0 defective. So suppose I can put the value x equal to 0, can take it up to this, fill the series. So I can take it up to 10. So there can be 10 possibilities because we are drawing the 10 matchsticks. So there can be the defectives can be present from 0 to 10. Now we will check how many times we have obtained the 0 defective, exactly 0 defective. So for this, again I have to make use of the countif statement. So, and again I have to use the countif statement and select this comma and have to give the this one. But before this, I have to reference it, because this I have to use again and again. I don't want to change this. So as this has to be used for each value for determining the defect. So I reference it. Now I can. So this is a, so 0 has occurred 4 times. So I just drag it down to see. So exactly one defective. So we can see in the table also 2 times. So this is 2. This is happens 3 times, and likewise 3 has happened 1 time. And 4, up to from 4 to 10 matchsticks, we haven't found this number of matchsticks are defective, having more than 3 have been defective. So we have find 0 matchstick. So this we have determined. Now for determining the experimental probability, how we are going to determine it? We simply put the because we know the count 4, and how many times this experiment has been performed? 10 times. So this will remain fixed. Just determine the experimental probability for exactly 0 defectives. Then I drag it down. This is the value for the 1 defective, 0.2, for 2 defective, 0.3, and the 0.4 there is for 3 defectives, 0.1. So in this way we can determine the experimental probability. Now I am interested in finding the what is the theoretical probability or the Poisson probability. How I'm going to do it? So just have a look on the formula, Poisson distribution. This is the formula. This is the probability of determining the X event. So suppose this is X is a defective. So X particular defective, X equal to 0. So what is the exactly what is the probability of happening the exactly one defective? X equal to 1. So I can put X equal to 1 here. This lambda is, we have discussed, this is the mean or the average occurrence of the event in a specified time, and this E is the constant. So it is the base of the natural logarithm, and its value is 2.71828, which is known to us. And by making use of this, we can determine the formula. So first coming to the n. So because I am going to find the theoretical probability and compare it with the experimental probability. So what is the n? N is the number of the trials. So that has been, I can write it, n is 10 in our case. Then what is the p? P is the probability of finding a defect. So P is fixed because we have taken 300 matchsticks and 20 are out of 320 are the defective ones. So the probability is the 20 upon 300. So I can just give 20 upon 300. Sorry, 20 upon 300. So this is the probability. I am having the value of the probability, I am having the value of n, that number of trials has been used. Lambda. Lambda is nothing but the mean, and it is denoted by the n into p. Lambda is the n into p. P is the, what is the probability, which is already for finding a defect. So determine this. And again write this equal to this into this. So this is the probability. And X for finding the 0 defect, then 1 defect. So again I can just copy this, I can drag it down so that I can fill in this series. So this is up to exactly 10 defects. So what is the probability of theoretical probability or the Poisson probability for exactly zero defect. This is the lambda. This will remain unchanged. This will remain unchanged for all the instances. I can just copy it. This is the average occurrence of the events. This is remains the same. Now, for finding the theoretical probability, I am making use of the Poisson distribution, Poisson dot dist function in the Excel, and first I have to put the X. So for exactly zero defective, I have picked it. Then we have to see the mean. Mean is denoted by lambda and into p. So this is the mean. After that, because we have to determine the probability mass function, so we have to write false in it. So now I am having the value of theoretical probability. I am just drag it down. Now we have obtained the values of the Poisson probability. Now we are going to draw the Poisson distribution curve. So for plotting this, I am just selecting the data. This data has been selected. Go to the insert, then go to the all charts, and here I am going to select the so this is the curve. So I can name it. So this is the Poisson distribution curve. I can add. So this is for lambda equal to 0.66. This curve has been plotted, and we can add the axis labels. So I just selected. Axis titles have been added. Now I can. This is the probability. And here I can add the X, the appearance of the event. So for the zero defects, so X is a defects, zero defects, this is the probability. This is the Poisson distribution probability that we have obtained. This curve has been obtained. Now I can change the color of the font color to the home. Select this. So this shows the Poisson distribution curve. Suppose I want to compare my whatever the Poisson probability and the or the theoretical probability with the experimental probability. So what I'll do for comparing it, I'll just copy this values of the experimental probability, just paste it here, paste as values. This has been pasted as values. Now this I can wrap text. This is the experimental probability. Now if I want to compare the two probabilities, so I again select this, go to the insert, charts, so this is the curve that I have obtained. I can put the chart here at this side. So this is the comparative chart also has been prepared. So on this axis I can add the axis titles also. So this is the probability. So we have drawn the comparison of experimental probability with the theoretical probability. We have also seen in this lecture the what is the Poisson distribution curve of this lambda. This has we have drawn, and this is a comparative chart later on we have determined, and we have drawn and determined and see that the whatever the results that are obtained with the experimental probability are in line with the theoretical probability. So thank you for listening.